Welcome back. So, this is fourth lecture in this course and we were talking about probability assigner functions. Um, and the background why we need these probability assigner functions, I can revisit that a bit if you have forgotten about it, if you took a break between the second, third lecture and this lecture. This is because whenever you are doing an experiment, you are collecting some observations, then these observations must be coming from some true generative process. Okay. Now, our goal is to figure out what is exactly this true generative process, but you cannot know what is the exact truth that has generated this data. So, what we instead do is that we make an assumption, and this is very fundamental to inference, that although we cannot know the truth, but what we can do, we can infer the properties of the true generative process. How? We make an assumption that this true generative process is actually a probability assigner function of some form f with some argument parameter theta. Okay. So we assume that this is the true generative process f of theta. So, whatever observations you are seeing is generated by this, and what this function does, it assigns probabilities to events in your event space. Okay. But this probability assignment, it's constrained by three axioms of probability. So, you can assume anything about this true generative process, but it should satisfy certain constraints, which is that it should be constrained by three axioms of probability. Second, it should make sense, it shouldn't be arbitrary, right. Now, because this is just an assumption, someone else can make a different assumption as well. Let's say g of phi, okay, and claim that this data was actually generated by g of phi, not f of theta. Both these are probability assigner functions, and we are assuming that in both these cases that f of theta is a true generative process, and let's say someone else is claiming that g of phi is the true generative process. Now, what we do? We use the data to estimate what is exactly this function f of theta that might have generated the observations. So, although you know the functional form what is f, you still need to estimate what is the exact value of theta. So, given the data, you estimate true value of this parameter theta, okay, and then you make a claim that if these observations are generated by f of theta, then the true value of theta should be theta cap, okay, and by that extension you make inference about the true generative process. And here as well, based on data, you would estimate what is true value of phi, okay. This is called parameter estimation. So, based on the data, you are estimating what is this exact function f of theta. So, what is the exact value of theta that might have generated this data, and same here as well, okay. But now you also need to compare these two assumptions, that which assumption is better at explaining the data. So, if f of theta is better at explaining the data, then you would say that the more likely process to generate this data is f of theta cap, right, and that basically completes our inference process. Okay. So, that is basically the idea. So, what we see is that this whole process requires us to understand this probability assigner function, because you will need to make this assumption whenever you are doing inference. So, you will need to assume some reasonable probability assigner function. Okay. So, what are these functions actually? So, one thing that we saw is this, that they need to be constrained by three axioms. Okay. So, let us take some simple examples. So, let us say you are doing a coin toss experiment, that you are tossing a single coin, okay, one time only. So, you are tossing a coin, right, a single coin toss experiment. Okay. So, what are the possible outcomes you can get for a single coin toss? You can get heads or tails, right. So, these are two possible outcomes for a coin toss. What would be then event space? Head, tail, head, tails, and an empty set. So, these are all the possible events. Now, what kind of probability assigner function you can assume here? Okay. So, just before defining a probability assigner function, you should derive what constraint it must follow based on 3 axioms. So, we have seen a similar example in the previous lecture, and what we derived was something like this, that it should follow this principle, that probability of E1 plus probability of E2 equals to 1. So, this is the constraint that should be followed, okay, and also their individual probabilities are greater than or equal to 0. So, we need to define a probability assigner function accordingly. So, a very simplistic probability assigner function you can think of is this, that probability of any event E, okay, is given by a probability assigner function f of containing 2 arguments omega and theta, such that the value of the function is theta if omega is heads and it is 1 minus theta if omega is tails, right. So, depending on the outcome or the event, basically elementary event. What is theta here? Theta is the probability, underlying probability of heads, okay, and it should follow of course this constraint that should be greater than or equal to 0. What does it mean? It can have actually any value, but the only thing is this, that it should be greater than or equal to 0. So, for any value of theta this function would work. Why? Let us think of theta equals to 0.9. If theta is 0.9, what does it mean? That the probability of event E1 would be 0.9, probability of event E2 would be 1 minus theta, that would be 0.1. Okay. So, now their summation is equal to 1 and both are greater than or equal to 0. So, it satisfies all the axioms. Okay. If theta is 0.1 or 0.5, it still satisfies all the axioms. Okay. So, if theta is greater than or equal to 0, then it basically works for us. Of course, it should be also less than or equal to 1, because if it is greater than 1, then it wouldn't work. Okay. So, this is what we have. It is a very simplistic function that can assign probabilities to an elementary event heads and tails. It can, by the way, also assign probability of this event E3. How? What would be probability of event E3? Actually, you can write E3, which is basically heads or tails, as probability of E1 union E2, okay, which is basically, because E1 and E2 are mutually exclusive, that is probability of E1 plus probability of E2. And what is probability of E1 plus E2? 1. So, this event E3 would be assigned a probability 1, and this would be true regardless of what probability assigner function you assume. Okay. So, this is how you can assign, you can define a probability assigner function, or you can assume a probability assigner function for a single coin toss. Okay. By the way, this is only one type of probability assigner function you can assume for this. You can also assume some other function, we will talk about them later on, but for the same case, it is not necessary that this is the only assumption you can make. You can make a different assumption as well. Only condition is this, that it should satisfy 3 axiom, that is it, right. Now, let us take a slightly more interesting example. So, let us say rather than having single coin, you are tossing 2 coins simultaneously, or rather than 2 coins, I think it would be better to have, let us say you are tossing a single coin 2 times. Okay. Tossing a coin 2 times. So, that is your experiment. Okay. So, this is a single experiment where you toss a single coin 2 times. Okay. Now, when you toss a coin 2 times, it could happen that you get heads on the first toss, you get a tails on the second toss, or you get heads both times, right? So there are different possibilities that you can have. So what are all the possible outcomes that you can get in this experiment? If you toss a coin 2 times, okay, that would be your sample space. So what would be your sample space? You can either obtain head on both time, you get a head on each coin toss, or you can get head tails, or tails heads, or tails tails. Now this is your sample space. Now your sample space contains 4 elements, right? What would be your event space? It would be very big, by the way, now. So event space, basically all the possible subsets. First, you can think of these elementary events: head tail, tail heads, tails tails, right? And then combinations of these. So head and HT, HH and HT, HH and TH, right? HH, TT, right? HT, TH, HT, TT, right? Then what else? HT, TT, then TH, TT, right? And then you can have combinations of 3 pairs, right? So for example, HH, HT, TH, right, and so on. So you will have many possible events. Now, so this is your event space, okay? So let us apply 3 axioms here and what it would imply, right? So the second axiom would say that the probability that one of the elementary event occurs, let us call them E1, E2, E3, E4. There are 4 elementary events now. Okay? So probability of E1 union E2 union E3 union E4 is equal to 1. Okay, so this is what the second axiom says. Third axiom would say that probability of E1 union E2 union E3, because these are all mutually exclusive, would be equal to summation of their individual probabilities. Okay. So what it implies is that the summation of probabilities of these events would be equal to 1. Okay. So basically we concluded the same thing even for a 2 coin toss example, that the probabilities summation of probabilities of elementary events should be equal to 1. Okay. But how do we define a probability assigner function now? Okay. So one of the ways in which you can define a probability assigner function is this, that you similarly have a function, okay, f of omega, but this time you will need to have 3 theta parameters. Why? Because you will need to define probabilities like this, that the value of this function would be theta 1 if omega is, let us say, heads, and it would be theta 2 if omega is head tails, theta 3 if omega is tail heads, and 1 minus theta 1 plus theta 2 plus theta 3 if omega is tails. Of course, it would satisfy now this particular constraint that probability summation of probabilities of elementary events is equal to 1. That is fine, because if you sum them up, right. So if you calculate probability of E1, what would be probability of E1? What is event E1? This HH, right. Let me just rewrite it here. So E1 is basically probability of HH. Okay, so if omega is HH, then this would be theta 1. Okay, you can see here. Similarly, probability of E2 would be, what is E2? HT. So this would be theta 2 based on this function. Probability of E3 would be theta 3, and probability of E4 would be 1 minus theta 1 plus theta 2 plus theta 3. If you take summation of all these, then what you would get is 1, because when you sum them up, they would be equal to 1. Okay. So, this probability assigner function is fine, it works for us, right. So, it is satisfying 3 axioms and it is doing the job for us. Okay. But the problem here is this, that now your probability assigner function gets very inconvenient to write mathematically, because what just happened was that rather than tossing the coin one time, you are tossing it just 2 times, and because of that now you are writing 4 rows for this probability assigner function. What if you toss it 3 times? Okay. What would happen if you toss it 3 times? In that case, situation would become even more difficult. Now your sample space would be HHH, HHT, HTH, HTT, THH, THT, TTH, TTT. Should be 8. Now 8 possible outcomes. You are tossing the same coin 3 times. So that's your sample space now. Now what would be your probability assigner function here if we follow the same approach? So it would be f omega, and theta would be now theta 127, because that many parameters you will need to define in the same way. So theta 1 if omega is HHH, theta 2 if omega is HHT, theta 3 if omega is HTH, and keep going on like this until you reach theta 7 if omega is TTH, and finally 1 minus theta 1 plus theta 2 plus theta 7, okay, if omega is TTT. So, you would have actually 8 rows in your function. Okay. That is bad, that is very inconvenient to write this function. Okay. We need to figure out a better way. Okay. Otherwise, it would be very difficult and very messy to write these probability assigner functions. Okay. So, what is the better way to write these probability assigner functions? Let us see. So, the problem we are facing so far in defining these probability assigner function is because of the fact that the outcomes that we have, or the elementary events that we have, are categorical by nature. Okay. These are not numeric. This is a function, remember, it is a mathematical function, okay, and it takes some arguments theta and omega. For theta, you would have some numeric values. Theta is anywhere between 0 and 1, and you would have some numeric value. So, it is fine for theta, but W does not have a numeric value. Okay. It is an elementary event. So, it can have a value HHH, HHT, HTH, and what do those values mean? Each value is a category. So, whether you would obtain HHH or you would obtain HHT, so each value is a category. So, it does not have any numeric value, and that is the problem, because if you do not have numeric value, then you will need to write a statement using these if else statement. For this category, this would what the function would do, for this category this is what the function would do. Okay. So, the only way we can get rid of this problem is that rather than having these categorical values for omega, right, can we define this function on a numeric space, not on categorical space. Okay. And how we can do that? If we can somehow transform this sample space. What is our sample space? HHH, HHT, HTH, HTT, THH, THT, TTH, TTT. If we can transform this sample space to another space which is numeric. Okay. So, if you can somehow transform this categorical space or this discrete categorical space to a numeric space, a more convenient numeric space, then we can easily define our probability assigner functions. How? So, let us say you define a function Okay. And what this function does, let me call this function by, let us say, capital X. And what this function does is that it takes this thing as an argument, okay, and gives some outcome in the numeric space. But how it can do it? The function would have to be of this nature. Let us say the function counts the number of heads in the possible, whatever possible outcome you have here. Okay. So, that is what this function does. It takes this thing as an input, each possible outcome as an input, and it counts the number of heads in that outcome or in that whatever argument to give you an output, right. So, how many heads HHH has this particular outcome? 3. So, this function will give you an output 3. Then it takes HHT and it would give you an output 2 because there are 2 heads. Basically, it is counting the number of heads in each outcome, okay, outcome of your of your experiment. Right. HTH 2 heads, right. So, basically, you can connect it with the same element here, right. Then HTT has 1 head, okay. Then THH, it has 2 heads. THT, it has 1 head. TTH, 1 head. TTT, this is different, 0 heads. Okay. So, what we have done here, using a function which counts the number of heads, we have transformed this categorical sample space into a numeric space. Okay. Now, treat these values, the values in this set omega x, okay, as the possible outcomes from this experiment. What these values say? Well, if you toss a coin 3 times, then either you would get 0 heads, or you would get only 1 head, or you will get 2 heads, or you will get 3 heads. That's it. That information is sufficient for us. Okay. Well, that would depend on your theoretical question. Sometimes you might be more interested in number of tails rather than number of heads, or number of consecutive heads, right. So, you can define a function accordingly based on what you are interested in. So, let us say you are interested in how many consecutive heads you will get if you toss a coin 3 times. So, you can do that. So, define a function in such a way that counts the number of consecutive heads. So, in this case you are getting consecutive heads 2 times, right. In this case you are getting it 1 time, in this case 0, 0, 1 time, 0, 0, 0, like this, right. So, you can define any kind of function you want. So, what this function is doing is that it takes it basically maps your sample space to another space which is numerical and convenient for defining probability assigner functions. So, it maps your sample space to another space omega x. Okay. How? Such that if, let us say, so if omega is an element of your sample space, original sample space omega, this is small omega is a member of capital omega, then x of w is equals to small x, such that small x belongs to omega x, right. And how exactly it works? That depends on how you define this function. So, you can define this function x of omega like this, that it would have so let us think of proper function. So, that x of omega equals to summation from I equals to 1 to n phi of omega I, okay, such that omega consists of outcome on each coin toss. So, let us say omega 1 indicates outcome on first coin toss, it could be either head or tails, omega 2 indicates head or tails on the second coin, omega 3 on the third coin, right? Phi is an auxiliary or intermediate function, and what this function does is this, that phi of omega I equals to 1 if omega I is heads and 0 if omega I is tails, right? So, this is how I defined a function capital X which maps your sample space to another numeric space omega x. So, the values of this function x would be the elements of your another well behaved numeric space omega x. Okay. And the example we have taken was of 3 coin tosses where your actual sample space is HHH, HHT, HTH and so on, right. It had 8 possible outcomes. So, consider this HHH. Okay. So, this is omega. So, if omega is, let us say HHH, okay, then you can call this is omega 1, this is omega 2, this is omega 3. Think of it as a vector of outcomes on each coin toss. Okay. And you can define phi of omega. So, phi of omega would be basically the phi of omega would have value 1 if the outcome is h and 0 if it is t. So, it should be 1 1 1 like this. So, phi of omega would be a vector containing 1 1 1. Okay. So, x of omega would be summation of phi of omega I. Okay. So, in this case phi of omega I has values 1 1 1. So, you basically sum these all these 3 values. So, you will get 3. So, f x of omega is 3. Okay. So, basically this particular outcome HHH would be mapped to 3 in your another space omega x, right. So, this is what we were doing here. So, we mapped HHH to 3. So, this is what this function does. It basically counts the number of heads. Okay. So, I have showed how you can write the function mathematically, but intuitively what it means is that you are counting the number of heads. You can have a different function that just counts the number of tails. Okay. This function x which maps omega to omega x, this function x is called a random variable. Okay. This function x is called a random variable. So, this is what we use to transform a categorical space to a more numeric well behaved space or some another space. You can transform it to any space. So, the function that we use is called a random variable. Okay. So, you might have heard this term random variable, okay, but it is not something mysterious or very complex, it is just a function. Okay. Random variable is not a variable or something random, it is just a function that takes elements, that takes the members of your sample space and gives you some numeric values. Okay. So, basically it is a function that maps your sample space to another well behaved numeric space omega x, that is it, right. And you have seen the utility of a random variable. If your sample space has categorical values like HHH, HHT and so on, it can transform them to values like 3, 1, 2, 0, right. How? You can just count the number of heads. You can define a function which counts the number of heads in each outcome in your sample space. So, a random variable is just a function that takes the element of your sample space as its input and gives you some numeric value as the output. And why this is useful? Because x gives you these numeric values. Okay. So, you define a probability assigner function always on the values of the random variable. What are the values of the random variable? Basically, whatever is there in this another space omega x, right. So, whatever values output you will get when you apply this function to omega. So, the probability assigner function is always defined on the values of the random variable, which was because these are numeric and well behaved, right. So, that is the idea, and that is why you will see that the probability assigner functions are written like this, f of x theta. Okay. So, rather than w we write x, because we are defining always it on the values of some random variable x, that is what it means. Okay. So, we will discuss in more detail what are these random variables and why they are useful, and there are different types of random variables that you would use for defining different types of basically to make different types of assumptions about the probability assigner functions. All right, thank you very much. So, this is it for this lecture. I will meet in the next part. Thank you.